So these are some derivatives of the special functions that you'll need to know on the exam. For example, we have the derivative of tangent, the derivative of cotangent, the derivative of cosecant, the derivative of a to the x, the derivative of the inverse of sine, inverse cosine, inverse tangent, inverse cotangent, inverse secant, and inverse cosecant.
Here we have the rules for the derivatives of inverse functions of x. We find that for any given function f of x, whose inverse is the function g of x, then the derivative of g of x is equal to 1 over the derivative of f of x at g of x. What does this mean? It means that for any function f of x, whose inverse is g of x, and contains the point a, b, the inverse g of x contains the point b, a. Thus, the derivative of f of x at point a is the inverse of the derivative of b of x at point b. So 1 over f prime of b equals g prime of a.
Alright, now we have L'Hopital's rule. So if the limit as x approaches a of f of x equals the limit as x approaches a of g of x, if that equals 0, then the limit as x approaches a of f of x over g of x equals 0 over 0, which is indeterminate form. But if the limit as x approaches a of f prime of x over g prime of x exists, then the limit as x approaches a of f of x over g of x equals the limit as x approaches a of f prime of x over g prime of x. If the limit as x approaches a of f prime of x over g prime of x is also indeterminate, repeat the whole process. Two forms of indeterminate form used on the AP test are 0 over 0 and infinity over infinity.
Alright, so now we've got the mean value theorem. The mean value theorem simply states that if you have any function which contains 2 points, q and p, then the slope of the secant line between q and p is at some point matched by the value of the slope of the tangent line at some point between them. So for every point p and q, there exists a point c between them, for which the secant slope is equal to the slope of the derivative at c.
Alright, now we have Rolle's theorem, which is pretty much the same as the mean value theorem, but for 0. So say we have a graph, and there are 2 points, f of a and f of b. If f of a equals f of b, then we know that the slope between those 2 points, the secant slope between those 2 points equals 0. So therefore, there must be a point c in between where the derivative equals 0.
Alright, now we've got implicit differentiation. Some functions have both x and y on both sides of the argument. What we need to do here is we need to treat y as a function of x and then find the derivative that way. So given a function, say x squared plus y squared minus 9 is equal to 0, all we do is we take the derivative of each argument in the function and treat y with a chain rule. So we do 2x plus 2y times the derivative of y minus 9, or the derivative of 9 is 0. So then we solve for dy over dx, and we get dy over dx equals negative x over y. Alright, now we've got derivatives of parametric curves, which are pretty simple. All we do is we take the derivative of each function that defines both the x and the y, and then divide the y by the x. So we take dy over dt and dx over dt, and that describes the rate of change of y with respect to x. We can also do that again, which gives us a slightly more complicated thing, but it's the same.
Okay, so now we have an example. Say we have p equals x of t comma y of t, and x of t equals 2 sine of theta, and y of t equals cos 2 theta. So we're going to take the derivative of y over, so dy over d theta equals dy over d theta over dx over d theta, which equals negative 2 sine of 2 theta over 2 cos of theta. So we simplify that and we end up with negative 2 sine of theta.
The end! Yay!